This side event is dedicated to the Euro Data Cube's freshest functionality, which we call Bring Your Own Algorithm. Before we go into more details about that, I would just like us to go quickly through the agenda for this side event so that you don't get lost in the details, because some of the presentations will be rather detailed. I will start with some high-level introduction to tell what Bring Your Own Algorithm actually is. And probably for those of you who have listened to Stefan in the plenary session, that might be a little bit boring, but for the rest, it should give us a good basis or the framework for all other presentations. Then we'll have two real-world showcases, which already use the functionality. And the first presentation will be given by Alessandro from Rea Group, and the second one from Maxime from Sentinel Hub. After that, we will go into much more technical or much bigger level of details. And if we all were at Esrin today, this would be hands-on sessions. But now we do not expect you to follow along. Yet we did prepare it in a way that you could do so with the help of the recording in case you want to do so after the event. There will be 3 presentations. Max will first guide you through the algorithm consumer flow, showing you the EDC browser app. Then Alicia will show you an example of an algorithm which uses Xcube processing service. And finally, Stefan will guide you step by step through the process that you need to do in case you are interested in bringing your own algorithm to the EDC marketplace. We will conclude this beautiful, interesting, and long day with a Q&A session. So I invite everyone to just post your questions in the chat. I will collect them and we'll address them at the end. I shall also mention that we plan this event to be approximately 1.5 hours long, so a little bit more than what was officially announced. Okay, I think I covered all the logistics. So let me first explain a little bit what was the idea behind the Bring Your Own Algorithm functionality. We all have been in the remote sensing field for a while, and we know that there is a lot of algorithms being developed and a lot of effort goes into that. A lot of expert knowledge is also needed to develop algorithms. Still, and yet, they are usually run on quite small test areas and shared within rather small communities. So usually it's just with the partners on the project or maybe within the research group. And oftentimes the results are just end up in a thesis or in a paper. Recently, it's quite popular to push your code on GitHub, but then most of this code is never run by anyone else than the author. We often, when we talk to people, to scientists, we often hear that they kind of know that they should move their processing to cloud, but how to do that? So in all these algorithms, we saw quite some potential, which is not used. And thinking about this, we realized that if we only know how to make it easy to run these algorithms, we could tap into this potential. And with this in mind, we started with developing it, but we did not start completely from scratch. We did have Euro Data Cube services in place already. So those were Sentinel Hub for serving raster data, GeoDB for serving vector data, then Xcube for the advanced processing, and the processing services such as EOX Hub with the hosted Jupyter Hub environment. And we already have had some interfaces in place, Python libraries with which you could interact with the services, OGC compliance services, and different APIs. Besides that, we also have operational marketplace, which will come quite handy now that we are promoting the Bring Your Own Algorithm functionality. So in this family of services, we now added the option to host and run custom algorithms on the platform. We will go into much more technical details later on. But it was not just the technical side of the story. There was also a little bit more business side of the story that we had to think about. And it was what are the relationship between the parties that are part of this process. And the way we structure that is that we have two types of users. We have algorithm consumers on one side and algorithm providers on another side. In the middle, you can see there's Euro Data Cube, bring your own algorithm platform. So there is no direct contact needed between the consumer and provider, but they both just interact with the Euro Data Cube. Now, if we look at the algorithm provider side first, so bring your own algorithm is what we offer to them. Once they have their own algorithms, they bring it to the platform. They have to provide descriptions and establish pricing for that. And then, so this goes to the platform directly, but somehow behind the scenes, we also have a commercial agreement with each of the provider in which we specify the responsibilities between us and them. This is published on the link given below. Now on the other side, we have algorithm consumers. And for them, the offering we have is, well, get insights on demand, right? So you can run this algorithm and then you end up with some data. Now, in order to do that, you need to get some credit somehow. You can purchase them directly on the platform, or you get some sponsoring, for example, from Network of Resources. And once you have that, you can simply go to the platform and order your algorithm execution. So these are the, let's say, relationships between the involved parties. Now, as an algorithm provider, what is it that you really need to do? This will be in the details presented by Stefan at the end. But in principle, you have to build your algorithm. You can do that on the EDC with the tools we have in place, or completely independently from that. But then you have to onboard it. So Stefan will present this in 7 steps. And once it's there, you can, let's say, forget about it. It lives there and users can enjoy it, use it, buy it. On the other side, if you are algorithm consumer, what you need to do is you need to have an EDC account. Then with that already, you can browse through the data available and through the available algorithms. And as I said before, once you have credits, you can, of course, order the execution of these algorithms by selecting it and input the values, and you end up with the newly created data. And this part will be presented by Max later on. So there will be much more details. I will stop here and give word to other presenters. I collected some useful links that I'll post in the chat because presentations will not be available to participants, so that you have them collected. Now, I suggest we continue with the first real-world showcase. So I'll stop sharing my screen and we'll ask Alexandra to take over. Alessandro, we can't hear you, so you'll have to unmute yourself.
Yeah, yes, you were right. So thank you, Hania, very much for the introduction and for the opportunity to present how we integrated our algorithm on the EDC. I start sharing my screen, so we can start now. Let me see if you can see something.
Yes, it works perfectly.
Okay. So my name is Alessandro Scremin. I'm an EO expert engineer and working for a group. And I'm here presenting, let's say, the first prototype and the predecessor for the Bring Your Own algorithm developed by by the ADC, presenting a real use case that we provide for some kind of indicators for the airports and harbors. We will see, for example, why this need as born and was asked for, how it was implemented in the ADC workspace, and what are the outputs of this algorithm implemented, and the workflow that has been implemented in a real use case for the vessel traffic detection and parked airplanes detection. So the concept right from the RACE, Rapid Action on Coronavirus, and the O initiative. I won't say too much on this because tomorrow there will be the presentation on a key session. But let's say that it is to provide information to evaluate the impact of the pandemic on the economical and environmental aspects of our life. But in particular, we were involved for monitoring the ports throughputs, so the number of ships at different piers, and the airports and the airports. So what we to implement this to provide this indicator, we use several platforms, several services or workspaces in the ADC. So the OX workspace, the Sentinel Hub, and also the GeoDB. The ADC allow us to provide our algorithm, to implement our algorithm inside this framework, and to be able to, let's say, maintain the rights of this algorithm. So not to expose to the users the algorithm itself, but the results of it and the communication between the ADC and the user request. So what was very interesting was the use of this headless execution, because we usually run mainly application on web browser, and this cause very often that you need a permanent connection to run the script, or you don't have much control about what are the issues that may cause the script failures. And so the headless execution allow us to run also complex scripts without having problem about the stable connection or issue with the connection, or stay continuously on the platform to make it run. It allows also to share the algorithm and to interact, let's say, with the algorithm to provide the inputs that are needed in a way to customize also the request and the use of the algorithm, the request on the users. And also it allowed to run complex scripts without caring about timeouts also of the web, and to make a kind of high massive training algorithms. To make that, it was use the Postman platform, let's say, libraries, APIs, which allow to set a body in which there are information about the position of the script and the parameters that are needed. And then it allows also to have information about the status of the jobs that have been triggered with the algorithm, and to know if they are completed or not completed, if they are failed, how long does they take to run. So you have a kind of control of the status of the single jobs. This is an example of how we provide the parameters to the algorithm. We use the Jupyter Notebook made available by the OX workspace, and in this example, you saw that we set the dates, the time range that we were interested in. This case was September to 2019. Then the cloud coverage, and some other parameters about which dataset in this case was Sentinel-2. And then all these parameters, the output of this, let's say, script to have this kind of information has been packed in base64 and then sent to the UPS point where the algorithm is ready to receive the inputs and run the processing, and then the outputs were provided in the S3 buckets. That is another space provided by the OX workspace. Then during this test, as we were the predecessor, we try to make also some experiments because we need more and more power, because the request of the training dataset became very high to allow to improve the precision of the output of the algorithm. So we also request an extra plan further to the standard one, in which we start from one GPU, that is the standard plan. Then we request ad hoc plan that was provided with 4 GPUs and the same storage and CPUs, and the 4 times the CPUs and the S3 bucket. This was because we needed a massive training for our network, for the ship detection and for the apron detection. And so we need to train this RCNN ResNet 109 architecture. And here you see some example that how many images or patches that that were needed for the training. In this case was for the apron detection training. It was 144 images that were cropped in patches of 124 pixels for 124 pixels, resulting in 852 patches. This caused a lot of time for us to wait that the training was complete, and it was around 240 seconds. So we asked for the extra plan, and we noticed that the provisioning of 4 GPUs and 60 CPUs allow us to reduce the time quite consistently. Even though we didn't see a direct connection between the number of GPUs and the improvement, we find out that a trade-off with 3 GPUs that allow us to fall down to 90 seconds to train one epoch. Then if you consider that for a quite good training, we needed at least 50,000 or 20,000 epochs, you can understand that in the first case with 1 GPU, it was almost 1 month. And in the last case, we reduce this to 1 week and a half. And we also use the GeoDB functionality of the ADC, because the output of our algorithm has to be ingested in the GeoDB to be gathered, to be presented in the dashboard, in the race dashboard. And so, for example, here these are a sample of tables that the database that have been generated, and table with several indicators, because there was not only our indicators that we were working on, but also others from other providers. Then this is just an extract of what are the information that are inside the file store in the GeoDB. And in that case was to have the time series of information that we will see later. In this case, it was possible also to ingest the shape files, and so to print also some very quick representation of this shape file. So now we are right to the real cases. So what are the outputs of all this process that were put in place? And these are the extracts from the race dashboard, because the final results was displayed and showed in the dashboard. So, for example, for the vessel traffic indicator, we compute the analysis of the number of ships that were at several piers. So the metallic ore piers, the non-metallic ore piers, and the oil stopped pile. for a period from December 2019 to present, because we are still working on, we are still providing updated information for this indicator that is run on weekly basis. Of course, it depends on if the image is available or not. And they provide also a GeoJSON with the bounding boxes of the detection. Here is a list of the airports that we are monitoring. Just a quick view. How is the dashboard? Just to raise kind of interest on it for tomorrow. This is the results of the time series that were provided with algorithm. That was CSV with all the detection dates and the number of ships, the acquisition date and the number of ships detected for that acquisition date for several ports. And here you see several real cases example of the dashboard. So this was the port of Hamburg on the 28th of June, based on Sentinel-2, and you see in orange the bounding boxes provided by via GeoJSON, via the use of our algorithm. So it's the output of our algorithm. Another case is here for Ghent, and you see you can see some zoom about the detection. Here is for the port of Genoa in Italy. Of course, there are some false negative, but yes, it depends on the training itself, on the number of training, but also on the spatial resolution of the images that in this case are all Sentinel-2. So sometimes it's very difficult to detect some ships close to the harbor, but we are working on improving also the algorithm. Then I was asked the next investigation about the impact on the Suez Canal. This is not present on the race dashboard, but we use the same algorithm and the same workflow. And here you can see that the area is very, very wide and covers several degrees. And you can see some samples on the area in the harbor, but also on the ships that are waiting on the open sea, for example, and another area here that are waiting to enter the canal from the other side of the entrance of the canal. And you see how the algorithm was able to detect and provide information of the detection. The same algorithm was trained. The same network was trained also with dedicated annotation for the parked planes. And so here you can the time frame that has been considered is always the same, run on a weekly basis when images are available, because if they are too much clouds, they are discharged because it's not possible to count objects through the clouds with Sentinel-2, of course. And the sites monitored were around 30, spread all around Europe, as you can see here. And also in this case, we have provided the time series, and you see the density of the bars that change on the sites, because there are sites that suffer of cloud coverage and other sites that are almost cloud-free all the year. So you can see also this density that provides you information about how many images has been used for the time series generation. And also in this case, you see the output of the algorithm with the detection. You can see in Madrid, you can see in London Gatwick, and you can another case in Madrid Barajas Airport. The interesting part of all of this is that the algorithm was a kind of copyrighted, so it was a kind of black box for the user. So it was protected inside the environment, and was put in place this VPS and endpoint to trigger the processing of this algorithm, and to provide the necessary files to be shown on the race dashboard. We are not in the marketplace yet, but because we are improving it, and we were kind of the predecessor of this bringing our own algorithm, and now there are also several other cases that later will be shown, and also tomorrow will be explained. And yes, the results are very nice, and the possibilities are really interesting. So I think I'm finished. So I thank you all for the time, and I bring back the floor to Anya for the next.
Thank you very much, Alessandro. Quite interesting use cases. And
Thank you.
cool. I suggest that we just continue with Maxime. Maxime, I will make you a presenter. Here, I think you should have an option to share your screen. It's coming up.
Do let me know when you see my screen.
We do.
Yes.
Go ahead.
Okay, hello everyone. So my name is Maxime Lamar and I'm working for Sentinel Hub here in Austria. However, this presentation is on behalf of the entire consortium that's behind the Eurodata Cube, whose logos are listed at the bottom of this slide. I'd also like to dedicate this this presentation to my colleague Chung, who's probably done more than 95% of the work here. I'm just a messenger. So in this session, I am going to use a concrete example to show you how you go from an idea to an operational product. If you were at Phiweek 2020, you may have already seen a presentation of the Sentinel-2 truck detection algorithm and wonder why we're presenting this again. Or you might think, why would someone from Sentinel Hub present an algorithm that was actually developed by Henrik Visser? I'm actually here to tell you a story, and I'm going to take you on the journey that starts from a brilliant idea and that leads to the possibility of purchasing a product on an online platform such as EDC. So in this presentation, I'm going to describe quickly the algorithm and show some results to remind you what the Sentinel-2 truck detection algorithm is all about. I'll then show you how we optimized the algorithm to upscale it to be able to run it over large areas and on demand. And finally, I'll show you how easy it is to onboard an algorithm such as this one on the Eurodata Cube platform. In 2020, in partnership with ESA, Sentinel Hub, and the Eurodata Cube, a custom script contest was launched, focusing on how satellite data could help monitor and mitigate the COVID-19 crisis. There were three categories: the economic side of things, the human activity distribution, and the agricultural activity. The best overall idea was awarded to Henrik Visser, who at the time was a master's student at the University of Würzburg in Germany, for his truck detection sensing trade from space contribution. How does this algorithm work? You'll be wondering, how do you detect a truck which on average in Europe is around 13 or 14 meters in length in a Sentinel-2 image with a resolution of 10 meters? Here I've shown a Sentinel-2 image of a motorway, which is just north of Darmstadt. And just looking at the band 4, there's no way to tell if there are trucks on this motorway or not. The algorithm cleverly utilizes two features that are part of Sentinel-2's detector. The first one being that there's a small delay between the acquisition of the bands. Notably in the visible, there's a delay of about half a second between the blue, the green, and the red band acquisitions. And there's a slight interband parallax shift due to the layout of the sensors, which are shown in this picture. This is most noticeable with objects that are above the ground, such as airplanes. Here's an example of an RGB color composite of Sentinel-2, where you can see that a single plane seems to be 3 planes of different colors. It's quite fun to look out for those in satellite images. But the concept that Henrik used was the same for detecting trucks, mainly using the time shift between the blue, the green, and the red bands. You can see the trucks if you look at RGB color composites because they appear as small rainbows of colored pixels. The method Henrik used to detect trucks was first to reduce the area of interest, or the analysis area, to the roads using OSM data to narrow down the analysis, and a road mask derived from Sentinel-2 images. And then a combination of ratios between the bands to identify clusters of pixels that could represent trucks. The last step is to vectorize these detections and generate a point layer where the detected trucks are located. This is an example of what an output of the algorithm looks like. On the right-hand side, you have the points plotted over the corresponding Sentinel-2 images. And on the left, an example of a geopackage file which contains features that are classified per detection date. When we were looking into the algorithm to onboard it onto the ADC, we were interested in seeing how the algorithm performs. So we run our own little test over a small area, which is located between France and Spain. It's one of the busiest motorways in Europe because all the traffic of the trucks bringing the fruit and vegetables produced in Spain to the rest of Europe go through this motorway. We did it on purpose to pick a tricky scene, not the easiest. We wanted to make our lives hard. We picked a scene that had some cloud coverage, as you can see in the picture top right. Even though it's not the easiest of scenes, the algorithm detected roughly 60% of the trucks on the motorway. But recently, I was delighted to see, I think it was through LinkedIn, that Anita Grasser performed a much better analysis of the algorithm in collaboration with Henrik and ASFINAG, which is the motorways of Austria. They used the data collected by the motorways across the network to assess the performance of the algorithm over 3 dates. They picked images that had low cloud coverage and worked on a 5x5 grid approach. The main findings of this analysis, which you can find on Anita Grasser's blog, are that the detection only works for large vehicles that move over 50 kilometers per hour, but this was already known. And as confirmed by our analysis and previously Henrik's analysis, there's a systematic underestimation of the number of trucks. On the map on the right-hand side, the negative numbers represent the absolute errors in the number of trucks detected per cell. However, the conclusions of this blog post were that the algorithm performs quite well, or at least satisfactory manner, with an R value of between 0.7 and 0.86. So we've got a great way of monitoring trucks over large scales from space. How do you go from a simple idea to large-scale monitoring? This is where our work came into play. Henrik started by submitting a custom script to Sentinel Hub Services. This is a piece of JavaScript which can be run through our APIs or within our EO browser. Here's an example of the detection of trucks within the EO browser. However, ESA showed some interest in the algorithm, and the consortium of EDC pushed Visser, or asked Visser, Henrik Visser, sorry, to deploy his algorithm on the Eurodata Cube. And he did so within a Jupyter notebook with a little bit more advanced methods in a Python script. And this version was also deployed to the race dashboard that Alessandro just talked about. Our job was then to take this algorithm and optimize it so that it would run in an efficient manner on the Eurodata Cube. And to do that, we broke the algorithm down into Python modules that interact within each other. When analyzing Henrik's code, the main bottlenecks that we found were first that the data for the roads is queried from the OpenStreetMap API, triggering downloads, which can be slow. That the methods used the Sentinel Hub Process API and were looping over tiles, which was also quite slow. And that the products were then computed locally from the raw bands that were downloaded. We analyzed the algorithm and came up with an optimized version where we were using three main tools that are available in the Eurodata Cube. Firstly, the GeoDB, which is an optimized storage database where we stored the OSM data and we store the results. We use Sentinel Hub Batch API, which is a cloud-based tiled parallel processing service for Sentinel-2 images, and generated not only the raw data, but added value information to be able to calculate the location of the trucks. And we built data cubes using the X-array technology to process this added value information. This slide shows the performance of the optimized algorithm on the Eurodata Cube. At the top, you have a graph where on the y-axis, you have the RAM usage, and on the x-axis, you have a logged number of UTM tiles. Just as a reminder, a UTM tile is 100 square kilometers. We ran this algorithm over a number of tiles for different time periods, so considering a whole year of Sentinel-2 data, 6 months and 3 months. For 3 months, the RAM usage was very low. It was a couple of megabytes. For 6 months and a year, you can see that the consumption is a little bit higher, but never goes over about 10 gigabytes. And you can see that this progression in consumption is not linear, so there's some effective parallel computing going on. If we look at the runtimes, the table at the bottom of my slide confirms this. The runtime for a single UTM tile is about 7 minutes, whereas the runtime for 100 UTM tiles, looking at a period of 3 months of Sentinel-2 data, is only 40 minutes. So it's not exploding like you would expect if you're using traditional processing methods. To bring the algorithm to market, I'm not going to go into too many details because the presentations after me are going to take care of that. I'd just like to say that the algorithm is available in the Eurodata Cube browser, that there's documentation that shows how to offer an algorithm on the Eurodata Cube, and there are 7 easy steps, as Stefan mentioned, and is going to present later on as well. The main key points to understand when you're bringing an algorithm such as truck detection to Eurodata Cube are that you need to define a certain number of input parameters. You can manage the results yourself or delegate the result handling to the Eurodata Cube. You also need to create an estimation of the costs in a Jupyter notebook. Once again, Stefan will go into more detail. And then you can easily publish your algorithm on the Eurodata Cube, have it integrated in the EDC browser, which Max is going to show you after me, and then profit from lots of clients buying the results of your algorithm. As it was said in the session earlier, EDC, bring your own algorithm, is there to make you rich. Thank you for your attention, and I pass the board back to Anya.
Thank you very much, Maxime. That was really, really interesting. But now let's look at this from the other side. Max, the next presenter, will show us how an algorithm consumer can now actually starts the execution of this algorithm. So I will make you a presenter, Max. Here you should be able to share your screen.
Try this quickly.
Yeah, it seems it's loading. Yeah, we can see it and we can hear you. Go ahead.
Perfect. Then, yeah, welcome everyone from my side. My name is Max Kampmann. I also work for Sentinel Hub in Graz. And in this part of the session, I will introduce our EDC browser visualization tool and show you how to navigate the interface. We'll briefly show you how to access public data collections with a couple of examples, and afterwards demonstrate the ordering process for one of the onboarded algorithms on EDC, which is the truck detection algorithm presented by Maxime earlier. So the EDC browser is available from the main menu tab on the left of the screen, as you can see here, and also deployable as an app in your personal dashboard through the marketplace. So in order to being able to also display personal data stored in EDC, we need to use the deployed app from our dashboard. I have prepared this already for this session, so I navigate to my personal dashboard and choose the deployed EDC browser app. So once you've opened the EDC browser interface, you can actually see the main menu on the left-hand side. Here you are presented with the two main tabs, of which EDC data contains all public EO data collections and allows searching and ordering for commercial data collections available in EDC, which are Pleiad, Spot, Worldview, and PlanetScope data. Then through the tab, you also have access to your personal user data that is stored in your data cube, like your commercial data, your data orders, XQ processing results, or geospatial vector data stored in our GeoDB service. The other main tab, called On-Demand Data, enables you to choose from already onboarded algorithms and trigger their processing for your area of interest, but we'll get to that in a bit. So first, I would like to take a quick look at some available public collections. So here we have access to global archives of satellite data, for example, from the Sentinel Hub, from Sentinel or Landsat fleets. And all the data collections can be displayed on the fly in the main window. And we can switch, for example, for the Sentinel-2 120 mosaic between different visualization layers here. Just as an example. So additional data sets like Copernicus services layers are also available. So let's quickly take a look at the Korean land cover data here for the area around Rome, just for demonstration purposes here. So after this, we will now switch to the on-demand data tab and order the processing of the truck detection algorithm and also visualize the results in EDC browser itself. So from the drop-down menu, we choose the truck detection algorithm, and the interface adjusts to our choice, and we can start to select or fill in all the required parameters for the algorithm processing. Before selecting an area of interest, let's first take a look at the area the truck detection algorithm is available in. So we switch this on, display available area, zoom to the available area. This is too zoomed in, so let me zoom out quickly. And we see that we can order the algorithm for most parts of Europe. The next step, we could zoom in, let's say, and select an area of interest right in the map. But for this demonstration, I actually prepared a GeoJSON for that interesting area that I will use here. Quickly import that GeoJSON. And you can see this is actually the location that Maxime mentioned already that we tested the algorithm on. Let's zoom to the AOI. So the bounding box covers the main transit route between Spain and France that Maxime already mentioned. That gives us enough material to actually showcase the algorithm and its results. So let's continue with setting the parameters. Let's set a time range of, let's take 3 months from the beginning of June to the end of August. Here. And whenever, I would like to note that whenever you have an input parameter that is not really self-explanatory, there's a little info button that provides a description for the respective parameter setting. And take the example of the OSM values, which would be the next parameter to fill in. This little description tells us that the trucks are only detected within roads that we obtain from the OSM service or from the OSM layers, and that we should specify each road type that we want to include in the processing of the algorithm. So let's go ahead for this run and select motorways and the trunk OSM street labels, road labels. Next, we would then go over to the maximum cloud cover percentage we want to allow on the roads contained in our area of interest. Let's take a value of 50% here. And then for the weekdays that we want the filtering to work for, let's choose Monday to Friday. So the only thing left to do here is actually hit the purchase button, which redirects us to the EDC bring your own algorithm checkout page to confirm the purchasing and the triggering of the algorithm. So if we do that, we're being redirected to the checkout site. And as you can see, there are a couple of steps to finish in order to trigger the processing of the algorithm. We have already provided all the parameters, all the input parameters through the EDC browser. So we just hit continue here. And then the cost estimation for the processing is triggered. And depending on the size of the selected AOI and the time range, which obviously adds another dimension to this estimation step, this might take some time. We should see this popping up any second. Yes, we see that a cost of 100 credits is estimated for the processing, and we are fine with this, and we continue. Next step would be choosing a delivery method. So we can store, for example, we can store the results in an S3 bucket, as you can see here. Select to receive the results as a one-time download, or store the results in our EDC GeoDB service, which is what we're going to select here. Having the results stored in GeoDB actually makes it really convenient to be consumed by applications. And this is exactly how the race dashboard accesses most of the data for the visualizations. And you can check out the dedicated side event on the race dashboard on Friday. So let's continue this step here. In a final step, we just have to confirm our choices and that we want to confirm and run the algorithm. We get notified that we can actually close this page because we'll get a notification once the processing of the algorithm run is done. And now, if you have the question, how do I actually get information about the processing status now? So if you navigate back to your personal dashboard in the My Data Product section, you have the Insights on Demand mentioned here, where you can actually check your credits with the transaction history of your ordered algorithms, and also link to the processing, to the Bring Your Own Algorithm results page. And you can see that we just triggered the Bring Your Own Algorithm track detection algorithm, and the execution is still pending. So for this demonstration, because we don't want to wait for the processing to finish, which might take up to half an hour for this size of an AOI, I believe, I will access the results in GeoDB through the EDC browser, user data tab, and from an earlier processing run. So let me switch back to the EDC browser here. I would just switch to the EDC data tab again. I have to confirm that I want to leave this on-demand data tab because I will lose my AOI. Then I navigate to the user tab, to the private collections. I open this GeoDB collection, and this GeoDB collection actually contains the vector point shape files. So it's loaded into EDC browser, and we can see the locations of the detected trucks with all the attributes from the underlying data frame that is accessible in the interface of the EDC browser now. And this would actually bring me to the end of my part of this session. And I would be happy to answer any upcoming questions later. And with this, I would like to give back the word to Anja.
Great, thank you very much, Max. Now I think we have the whole loop in. Good. We'll take questions at the end, as I said. So we'll continue with Alicia. I will make you a presenter. Here you go.
Yes, thank you. All right. share. All right. Hi, everybody. You should see my screen now, I hope.
We do. Yeah, we do.
Perfect. Thank you. So I'm Alicia. I'm from Brockman Consult, and I would like to take you from where Max left you, basically, and show you a bit the insights behind an algorithm. So I would like to tell you how we developed the MCI algorithm into the EDC browser, and we used Xcube processing to do so. So we will, in the end, look at the result of this ordering. So I'll not order this now, but just keep in mind we take a look at an area in Italy, so close to Rome. There are a few large lakes, which you can see in the bounding box. And these are quite interesting for MCI, which is maximum chlorophyll index. So let me take you to the Jupyter Notebook, which we use to actually develop the algorithm chain to include it into the EDC later. Like I said, we're going to look at maximum chlorophyll index. It's a great index because it's a robust indicator for critical eutrophication situations in any water body. And it's used to identify exceptional situations related to phytoplankton. Here you can see the formula. Don't worry about it. It's just to show you what it consists of. But you can take any formula you wish for your purpose. For our maximum chlorophyll index, we need the following bands. So we will take Sentinel-2 data, and we will need the three, so BO4, BO5, and BO6 bands, which have different wavelengths, as well as the scene classification data and a cloud probability data. Both are available within Sentinel-2 data. All right, so I talked a bit about Xcube processing. So, well, I mentioned it, so I want to tell you now a bit about it. So Xcube is a open source software. It's there to generate, manipulate, and analyze EO data. And the Xcube processing part is the ambition to bridge the gap between data access and the analyzers-ready products. Xcube is developed by Brockman Consult, and it's one of the approaches to integrate your own algorithm into the EDC marketplace. Let's have a look at the structure of an Xcube generator request. So it consists of 4 parts. You've got the input configuration, the cube configuration, a code configuration, which is particularly necessary for the algorithm development, and the output configuration. For the inputs, you could use different sources as an input data. So you see here Sentinel Hub data store, the geodatabase, or data stored in S3 buckets. We're going to focus on Sentinel Hub data in this example. So once you have your input data ready, or you know what you need, then you can worry about the part of putting your area of interest and choosing the time range. This all goes into the cube config. Also the bands you need. Then the code config is the user code. So that's the part where your algorithm kicks in. And finally, define where your data should go. So this is the output configuration. So what are data cubes? Some of you are probably very familiar with them, but I just want to remind everyone else, or bring it up to you. So there's data sets which are called data cubes, have more than one geophysical data variable, and they're multi-dimensional. So we've got here in the image of Xarray. Xarray is a package, a Python package which we use in Xcube. So we see here you've got a cube with temperature, precipitation, both of them have a layer of latitude and longitude and a reference, a time reference. Latitude, time, and longitude have to be present to create a data cube, and other dimensions may be present as well. All right, now that we have cleared all the basics, let's take a look how to develop an algorithm with X-cube processing. First, we're going to fetch a subset cube, which contains only the input bands we need. Then, based on that subset cube, we will develop the algorithm. And in the third part, once we're happy with the algorithm, we will package it and then run the generator service with the processing on a larger data set. So the fourth part is very convenient because you then do not run your algorithm on your machine anymore, but you send it to the X-cube generator service, which then provides the necessary RAM and CPUs. All right, so let's fetch the source cube. You can see we're going to import some packages. We select the bounding box. It's Lake Trasimeno, and it's one of the lakes in Italy. So if I zoom out, you can see it's within the bounding, within the selected lakes I showed you in the EDC browser. We just select one of them because the algorithm development happens on a rather small area. Well, let me continue here. We have to import a bunch of generator classes. I'll not go into detail here. And we have a helper function to calculate degrees from meters. But let's look at the generator object. So we here recognize some parts of the four parts I showed you about the request for the X-cube generator. So we've got the input config. We specify that we want data from Sentinel Hub. We also then in the cube config, like I said, we select the input bands. So we have the ones I mentioned above. And then we also select the time range. Here I chose July to August of this year. Then finally the output config. We're going to save this particular cube to our working space here. And then all these parts are taken together and sent to the cube generator request. So first we just generate the request. It's not sent yet, but we can check again. Sorry, that was quick. We can check again if everything's set all right. So here we see the store ID is Sentinel Hub. And the cube configuration, let's take a look at the variables. They're all there. All right, so then we initiate the local cube generator, and next we can request some information about the cube we want to generate. So it just says, all right, your request is fine. And then we're gonna request the data cube. I'm not going to do this now because, as you can see, the last one took 40 seconds. I have it here in my workspace already, so let's skip this part and take a look at the cube directly. So now we have the cube in our workspace and we have the necessary bands. So we can now jump into the algorithm development. Maybe we want to have another look at one of the bands to check out the metadata. You can, of course, do that. And also take a look at, plot the data. You can see here, that's our lake. It's this is a 100 meter resolution currently. And then we want to, so for the algorithm, we want to look only at water pixels. So the Sentinel-2 data provides us a scene classification flags, which have water in them. and we can use Xcube's mask set to derive them from the data. So you can see in the scene classification we have the water, and we can mask in the cube the water data out. Let me show you here. So now we have a layer where only water pixels are 1 and the non-water pixels are 0. All right, so now we get to the code. The details are not that so we will not look into the formula, as I said, but it's a Python function and it operates on NumPy arrays, and it returns in the end the maximum chlorophyll variable. So this is to compute the variable, but we want a data set to come out at the end. So we do have another helper function, which is called compute MCI cube. And there we include, so we give a X-array data set, which is our source cube, and an X-array data set comes out again. And here you can see the parts, for example, the water is included. So first the data is masked, and then the MCI variable is computed. So in the end, we just add in some attributes to it, and the result is that we get the source cube together with a new band, which is called MCI. So let's check out how this works. So here you see the compute MCI cube function, and I provided my source cube, which we looked at. And it calculates the MCI. So the new data set has our input bands and the additional one in it. And we can have a look at it. Oh, let me scroll a bit. And we can see that we have some data for the maximum chlorophyll here. We also can take a look at the time range, take a look at each of the timestamps to plot it to see that there's already a difference between the days in this 2-month time range. So now we come to the algorithm packaging. And as I mentioned in the beginning, there's a fourth component, which is called code config. This is needed to package everything and send it then to the Xcube generator service. And we provide it with our two functions, which were compute MCI cube and compute MCI var. And I want to mention that the code you can provide in different ways. So one of them is like we do. So it's it's from a callable and from code. And then there's also, if your code base grows bigger, you can do it from a file set or from GitHub archive, which is quite nice for versioning of your algorithm. So once we have this, we run the code on a larger extent. So here I've selected the same bounding box as we saw in the EDC browser. And next we put all components together and send it to the generator service. So here we have the cube config. We have the same input config as we did for our source cube. The output config, this time we will not save it to our local directory, but send it to a default bucket, which is called your data cube scratch. Data there is kept for 4 days. And then we create a service request. So we have input config, cube config, the code config, and the output config. Here we have to manually create the service config JSON. This will not be the case in the future. The environment variables are already there. It's just we need to put them into the config together. All right, and we have to initialize the cube generator. and then we can ask for some information. Now we're sending this to the Xcube generator service, and it will tell us how much our request will cost. So here you have a cost estimation, and it will cost us 80 processing units. And yeah, now we can go ahead and generate the cube. So this takes a moment, and I'm afraid I'm close to time and up. So I'll show you the result in the of the cube generation in the browser. So once you've requested the cube in the EDC browser, after a while you will get a result. And the result for the MCI cubes, MCI algorithm is that you will be told where it's located. So in this case, your data cube scratch bucket, and a link with a viewer is provided. So we can go to that link and already have a glimpse on the data. You can see the bands are here. We select maximum chlorophyll index, and it's quite neat tool because you can do some quick data analysis already, and it will, you can already investigate a bit. So we could create a time series and also compare it to a different water body, for example. And then you see in the time series that they have different values, and you can investigate a bit more to know if you're satisfied. And now I hand over to Stefan, who will tell you how to actually get the data, like your algorithm, into the EDC browser.
Great, thank you very much, Alicia. Let me see if I can switch the role for Stefan. Yeah.
Thank you, Anja. Then let me share my screen. Can you confirm that you can see my screen, please?
Yes, we can.
Perfect. Good. So welcome also from my side. My name is Stefan Achznit, and I'm working at UX, and I will continue the story of this side event now with how you can bring an idea codified as an algorithm to the Euro Data Cube marketplace, so that also other users, consumers, can discover and check out your algorithm to generate such data products based on selected custom input parameters, and to generate, as we call it, this bespoke data on demand. So what does it actually mean to become an algorithm provider, to become an EDC business partner? Also, my colleague Stefan Meisel already showed in the keynote today this diagram. So on the concrete interactions between you as a potential algorithm provider, the interaction to the EDC platform itself, and to us responsible to do the commercial, the accounting background work. And if you followed this keynote presentation before, you also know that as soon as a consumer checks out an algorithm on the marketplace, on the platform, to generate such a bespoke product, you as algorithm provider will generate revenue. So you will get quarterly usage reports, and based on that, you can then invoice real money, your margin. And if you follow this link here shown at the bottom right, you will find a PDF, the algorithm provider tech link. This provides all the necessary background information from business perspective, how revenue is generated, and more generally, what are your opportunities, but also what are the responsibilities when you take on the role of an algorithm provider. So this is let's call it the business side, and it's definitely important to understand the implications. But where I want to put focus now is more on the technical side, how you can develop and validate an algorithm. And so how can this algorithm finally be offered on the marketplace so that it is fully onboarded and discoverable for others to be checked out? So to understand how you can develop an algorithm, let's go one step back before. So let's do a short recap on the EDC platform. So this is again a diagram already shown today before. And what's important here is to understand that EDC provides you with several building blocks. So you can use API services like Sentinel Hub and GeoDB to incorporate them in your EO workloads. You can leverage processing frameworks like Sentinel Hub Batch or Xcube Gen processing for your big data workloads to delegate all these EO data processing, data pre-processing tasks further. So they are now out of your responsibility to manage. And you can orchestrate these workloads from a central place from EOX Hub, a cloud-based execution runtime. And exactly this notebook-based execution runtime is the main entry point where your workloads, your algorithms will get invoked. So either by yourself, this can be done, either by yourself, so this can be done either interactively via JupyterLab, as already shown before, or in a headless fashion using this OGC compliant API interface, which was also mentioned by Alessandro in the first presentation. Or, and this is now new, the same workloads, they can also be invoked by an EDC marketplace consumer if you have decided to offer your algorithm on the marketplace. So from coding perspective, nothing has to change. It is the EDC platform itself which will differentiate between these different invocation scenarios. So let's have a short glimpse into already onboarded algorithms and how they use the EDC platform. So we have an algorithm able to calculate cloudless mosaics based on Sentinel-2 data. We have the algorithm to detect trucks as presented before, and we have the MCI algorithm from the previous presentation. So these are 3 algorithms currently onboarded, and they all use different capabilities of the EDC platform. So the cloudless mosaicing, this is done directly within EOX Hub. The algorithm just goes to the satellite archives as available in object storage, downloads the data, and does the processing, the mosaicing accordingly. In contrast to that, the truck detection algorithm outsources this scene-based satellite data retrieval. It uses Sentinel Hub Batch instead to get all the necessary satellite band information pre-processed and made available as a multidimensional array, an X-array. And this means no nitty-gritty fiddling around here. So just get the data as you need it for further processing. And in addition, the truck detection algorithm also prepares the roadmap network downloaded from OpenStreetMap in GeoDB. Then it finally combines these data sets and derives the necessary insights, in this case, the detected trucks. And last but not least, the MCI algorithm, as just presented before. This uses the Xcube Gen processing service to generate data cubes, in this case in SAR format, by internally communicating with the Sentinel Hub API to retrieve the necessary Sentinel-2 data. And in this case, the full processing chain is outsourced to a managed system, to another managed platform. And EOX itself, it is just used to invoke the overall workflow by making the proper API calls. So to sum up, it is up to you, up to the algorithm provider to decide which API services and which processing frameworks to use. And you can always use additional ones, like you can go to the OpenStreetMap API, or you use your own task cluster, your own Spark cluster, your HPC system for the processing. So this is completely up to you, but what's important here is that you have to do your due diligence also if you really want to use such offerings. So they all have different license models, and the APIs give different SLAs. So this is always something you need to consider if you want to use third-party services and offer a product out of that. Good. So if you want to offer now on a EDC platform, yeah. So the first important thing is you need to write code, and the nice thing is you can use your existing know-how you already gained with the EDC services to write exactly this part. Yeah, the code is invoked from a Jupyter notebook, and this also means for your core processing logic, your core algorithm, this must not be developed in in Python. Yeah, you are free to use any programming language. You just need to invoke it from the Jupyter Notebook. So you can use Python, you can use Java, you can use R, whatever you like. And you can also use different libraries, machine learning libraries, PyTorch, whatever you need. Yeah. From platform perspective, all of that is all these things, they are treated as a black box you have to develop, which is fully under your control, but a black box with a well-defined entry point. And if you have defined these inputs, let's say, for example, a max cloud coverage, which is used to filter scenes, or in the case of the drug detection algorithm before, where you can select the weekdays, this must just be formalized in the way so we can finally use the information for the checkout in our UI. So as you can see here as an example, there is some meta information around the individual input parameters, but that they can be defined by you. And as soon as the algorithm get onboarded, this information is associated to the algorithm for a checkout. Good. Having these inputs defined, now we come to the step where you need to validate your algorithm, and you need to benchmark your algorithm, because it's important that you understand the behavior of the algorithm. So based on different input parameters. So usually it's a difference if you calculate over a small AOI or a large region or a whole Europe. You need to really understand what's happening internally, because only then you can come up with a proper pricing model. Yeah? And such a pricing model, this may be, for example, as simple as a price by square kilometer based on the selected AOI of the consumer. But it may also include other parameters. For example, in a drug detection use case, perhaps there is a different computational effort based on the selected weekday, because if you just select 1 or 7 days, there are different program logic will run and may result in a different price. And as soon as you have defined now the input side, you also need to properly describe your algorithm. So what is the kind of data which will be generated? Is this vector data, raster data, in which format? And all this information together with as a description, more or less the marketing information, this will be curated and published on a central place. And this is this your DataCube public collection repository, where all this information comes together, where you can browse it. And this is also the canonical source of truth for the EDC browser and the Euro DataCube marketplace to get the information from. So if you need some baseline how you should describe your algorithm, just have a look at the existing ones and get some ideas how it's done there. Okay, so there were many part mentions now. So now perhaps you are wondering how these things are all plugged together. How can you as an algorithm provider, for example, give a binding price estimate to the consumers if they check out an algorithm on the marketplace? So how is this done technically? Yeah? And therefore we have created a walkthrough example, a sample algorithm. This is also based on the MCI, but it's a more simplified version. And you can find it again publicly in GitHub in the Euro DataCube repo under this repository name, bring your own sample algorithm. And what you see here, this is the scaffolded structure, which is also provided by us during the onboarding. And your responsibility now is to properly fill up this the notebooks. And there are just two important files. On the one hand, you have the estimate costs notebook. This is the notebook which will be invoked when a consumer asks for a price estimate for his given input selection. And then if he decides to check out the algorithm, the other notebook here, this is just called notebook, this contains the algorithm code to finally trigger it. And let's have a short glimpse into that. So I just checked out this repository just mentioned, and I filled it up with a rather simplified version of a price estimate. So in our example algorithm, we have two input parameters. On the one hand, the AOI, and on the other hand, a spatial resolution. And these are just default values I use for development. And these are the values which will be then overwritten if the algorithm is run by a consumer. what I do now is I just use the AOI to do some simple area calculation, and I return a price. And again, the nice thing, all the things I can do here in the notebook. Yeah. And the same now, let's switch over to the concrete algorithm. It's not much more complicated. Again, you have the same input parameters. Let's run it perhaps to see what's happening. You have the same input values. You are setting up some logging, some out where the result should go, and then you do your core calculation. In this case, we are using the X-Cube Sentinel Hub bridge with the cube configuration. We open the data cube. We use the scene classifier for water to infer the water cube out of it, and then we do the calculation for the MCI as shown by Alicia before. We get a data cube and we visualize it, and then we store the result. So this is an algorithm which is run now in my notebook code. This is an algorithm I can trigger via an API in the same way. This is the headless processing, and I can decide to publish the algorithm now on the EDC marketplace. And as I have prepared it just to show that how the things are coming together, let's shortly go to the EDC browser. So at the moment we see the 3 algorithms here, and now I will do the API call to properly onboard the algorithm. So I have done all the sign-off procedures. I have signed the provider agreement. All the steps are done, and now I'm ready to onboard it. So let's trigger the call. And now if we reload the algorithm, and if we reload the EDC browser, we should see also our sample algorithm here. And you can see there are exactly 2 input values. There is the area of interest and there is the spatial resolution. This was exactly as we defined it here in our region. And now I'm able to check out the algorithm by just selecting an AOI, confirming the AOI, purchasing it, and then going through the individual marketplace steps to check out the algorithm. So this is just a short glimpse how the things are working in the background. And to have these 7 steps which were mentioned before, they are just summed up together in one on our EuroDataCube documentation page. So you can find the link here, and all the things I just presented, they are there on a step-by-step basis. Some are technical, some are business related, and you have just to go through the list and start the process to finally get hopefully revenue. Good. Thank you very much.
Thank you, Stefan. Good. That brings us to the end of what we prepared for this side event. Now, I would like to leave some time if there are maybe any question or any comment to what was presented. I know that attendees cannot speak if I don't unmute you. So if you want to speak, please write to the chat or just post a question or comment in the chat. No, it seems there are no real questions or no feedback, but I guess it's already quite late. So I would not want to prolong this too much. Still, let me just give a few more seconds in case anyone jumps in. Otherwise, I'd like to thank all the presenters. I have posted quite some links in the chat, so for those of you who are interested, please just go there. Those are good starting points. And in case you have any problems or questions, don't hesitate to get in touch with us. Thank you very much to everyone who participated. And I'd like to close the event with this. Thank you.